Howdy folks. So, in the last video we talked about classifying chemical reactions, how to balance them, and a little bit about driving forces. In this video we're actually going to break down the various reactions types. So we'll at least start, I'm not sure, we'll see how well it's going, but we'll at least start with precipitation reactions. Those are a little bit harder. So, with that in mind, first, before we get into precipitation reactions, we have to understand how a solution actually forms. What does it mean to be aqueous? Well, when a solid dissolves in water, we call that solid to be soluble. So just some quick terminology. If it were to remain undissolved, it is said to be insoluble. Please note, insoluble does not mean not soluble 100%. Insoluble means largely undissolved. Some trace quantities can dissolve, but the large portion of it remains undissolved. In fact, some reactions can be changed from soluble to insoluble or back through acid-base chemistry. We can make something dissolve in water and then precipitate from water, then back by just changing the pH. Just like, I think, crack cocaine. You change cocaine to crack by reacting and removing a proton, change it from an ionic solid to a purely covalent compound by mixing in sodium bicarbonate. And while this is drugs, this is something you can find out on Wikipedia just fine. Just look at the chemical formula and look at the chief difference, and it's really just there's an H plus here. When you mix in a base, you remove that and it changes its properties. Now, when something dissolves, the dissolution occurs because of the process called solvation. Basically, water is hydrating the molecule. Whether this remains a compound that is unbroken or it's an ionic compound that breaks up into its individual ions and dissociates. They are being hydrated by water. What is happening is that water is in such great quantities that it is completely enveloping the individual molecules or ions and separating them from each other. What makes a solid visible is that we have millions and billions of molecules all packed up together. When you start breaking it down into smaller and smaller bits, it becomes too small for the naked eye. We no longer see the individual atoms that are separated, and so the water is going to separate each individual atoms and surround it. Now, this separation and dissolution occurs because of polarity. Remember, we talked about polarity when we talked about Vesper models. But water is a polar molecule, with oxygen being negative and hydrogen being positive. This dissolution works by attraction of opposite charges. Water contains a partial positive charge around the H's and a partial negative around the O, as we see in the upper right the image. We use the Greek letter delta to represent the partial of the partial charges. We can give the size of the delta related to the size of the partial. But in this case, water orientates itself to put the negative charges near the positives and the positives near the negative. That water will naturally stick itself like a magnet to the atoms. The cations get surrounded by the partial negative of water, and the anions are surrounded by the partial positive of water. And even though a truly cation anion interaction is stronger than this partial charge, the fact of the matter is there's enough water that it can surround and remove. It can screen other molecules from each other, that it's going to block them out so you won't be able to see them. It's like the meme you may have seen, the trope of how many third graders could you take on? Yes, you could probably drop kick them all, but eventually you're going to get tired. Eventually they will overwhelm you. It doesn't matter how strong you are. If there's wave after wave of tiny little kids coming at you, they're eventually going to take you down. Eventually, assuming there's no things like fear and morale and all those things, but they can overwhelm you. Same way, water, there is usually 10 times, 100 times, 1,000 times more water molecules than there are of your solute, the thing that's being dissolved. And so the water quickly overwhelms the other guys. Even in non-ionic compounds, if they have a partial charge, they will dissolve. So things like sugar. Sugar stays as the molecule glucose. It doesn't break down, but it has a bunch of partial charges. It is an overall polar molecule, so it will dissolve. You get things like, a lot of different things will dissolve because of its partial charges. Ethanol is perfectly miscible in water because it has a polar OH group. Miscible, remember, means will dissolve infinitely in water. You can add enough ethanol so that water starts to be dissolved by ethanol instead of the other way around. But if they don't have any partial charges, they won't actively dissolve in water. So we can break down types of soluble compounds into 3 classes. We're going to ignore the insoluble compounds because we're only talking about soluble here. But while many compounds are water soluble, they don't always have the same properties. Most compounds we're going to assume are in this first category. Strong electrolytes. Electrolyte simply means atom capable of conducting electricity. In this case, to conduct electricity, they must have charges. Charges for the electrons to bounce around off of. So when a compound fully dissociates into ions, it will strongly conduct electricity, and thus will be a strong electrolyte. If I dissolve something in water, it dissolves 100% or near 100% and breaks down 100%. Now, on the flip side, if it dissolves but it does not break apart, because of that nature, it will not conduct electricity. It is called a non-electrolyte. Molecular or organic compounds are chiefly non-electrolytes. Things like sugar doesn't break down, and so sugar does not cause water to conduct electricity. However, there is a class that is somewhere in between. A compound that we'll learn about much later, not this semester, but they will partially dissociate into ions and water. So it will only weakly conduct electricity. These guys are called weak electrolytes. Now, you've seen some of these guys before. Acetic acid is such a weak electrolyte. You drink citric acid is still a weak electrolyte. We would not dare to drink it otherwise. It would burn our throats out. So it's tangy and tart, but not particularly dangerous as a weak electrolyte because it only produces a small amount of the acid that it's capable of producing. If I drink equal quantities of acetic acid versus sulfuric acid, one's going to dissolve my throat, the other is going to pucker me up, but otherwise leave me unharmed. That's the difference between a weak electrolyte and a strong electrolyte. Now, here are some examples. Strong electrolytes are composed of soluble ionic compounds and strong acids and strong bases. For that reason, they completely ionize in water. So sodium chloride is an example of a salt. Potassium hydroxide is a base. Sulfuric acid is a strong acid, so it's completely dissociate. Non-electrolytes are usually soluble molecular compounds like methanol and glucose, C6H12O6. Notice, no metals, and the H isn't out front. Now, a weak electrolyte have properties that are both ionic and molecular in nature. These are most often considered weak acids or weak bases. They ionize to a small degree but remain mostly intact. Acetic acid is a weak acid. Carbonic acid is a weak acid. Ammonia is a weak base. So these guys are examples of weak electrolytes. Now, these are a lot of rules. I do not ask you to learn these rules. However, Rule 1 and Rule 2 will serve us well. But let's read these. So, when looking at precipitate reactions, we're doing a double displacement. We are mixing a compound with another compound that are both aqueous. A precipitate by nature is an insoluble solid that forms out of a solution. It forms regardless of what you do, it's going to form. And so long as the product is insoluble, meaning if it should form a solid, it will form a solid. If you look at the double displacement, and it should be solid, it forms a solid. Now, there are some rules. There's also a table that will help you. Rules that will determine whether precipitation reactions should occur. The only two rules that are super duper important, because most of the time you'll get the table, is Rule 1 and Rule 2. These are the always rules. We need to consider whether a precipitation reaction occurs when we consider whether a reaction will occur. So, to do a precipitation reaction, you must first write the products of a double replacement or the double displacement. We're going to use the rules or table to find the solubility of the product. Now, here's an important thing. If any product is insoluble, a precipitation reaction occurs. If all products will be soluble, no reaction will be said to occur. If all are soluble, no reaction will be said to occur. So hypothetically, if I was given a reaction that said sodium hydroxide and iron chloride form what? I'm doing a double displacement, so I'm replacing sodium with iron. Iron is iron 2, so I'd have 2 NaCl, and then I'd have FeOH2 because hydroxide is -1. Then I'd look at these rules. So I'm going to read through the rules, though once again this is more than I ever expect you guys to know. Rule 1. Compounds containing group 1 elements or ammonium are always soluble. So any of the group 1 elements, lithium, sodium, potassium, rubidium, cesium, francium, are always going to be soluble, always. Ammonium and any of those elements, any compound will also always be soluble. So it doesn't matter whether it's ammonium chloride and ammonium phosphate, ammonium chromate, it's always soluble. So sodium hydroxide and sodium chloride are already soluble because the sodium. Rule 2. Anything containing nitrate, chlorate, perchlorate, or acetate are always soluble. So it doesn't matter whether it's silver nitrate or sodium nitrate, always soluble because of those weird oxyanions. Those 4 oxyanions are always soluble all the time. Now here's where we get into exceptions. Sometimes, but not always. That's why I don't ask you to learn these guys. Chloride, bromide, and iodide are usually soluble, except when it's mixed with these 3 heavy metals: silver, lead, and mercury. So mercury is right there over below zinc, silver is right below copper, and lead is right there below carbon, way at the bottom. Those 3 guys make solids of those 3 halogens. This one are almost always insoluble. Carbonates, sulfites, phosphates, and chromates are insoluble except where condition 1 occurs, which is group 1, the always solubles. So lithium carbonate is soluble. Sodium carbonate is soluble, but iron carbonate is not. So keep in mind, with the exception of group 1 and barium, hydroxides and sulfides are insoluble. So the reason why hydroxides and sulfides aren't mixed in with rule 4 is because they have another exception of barium. Still group 1 metals, but also now barium hydroxide is soluble. Means it dissolves. Barium sulfide is soluble. Now, this one's just making a special mention that lead, silver, and mercury are always insoluble except for rule 2. So not all the metals are always insoluble, but these guys are very insoluble, more insoluble than usual. And then finally, with the exception of these 3 compounds and compound 6, silver, mercury, and lead, all sulfates always dissolve. So sulfate dissolves except for calcium sulfate, strontium sulfate, barium sulfate, lead sulfate, silver sulfate, mercury sulfate. You might recognize lead sulfate if you know anything about batteries. That is the salt that forms in your car when you let it discharge too long. Of course, we use oxidation reduction to turn that back into solution. So that's not quite the same thing. But this chart serves the same purpose. Note rule 1 going across, rule 2 going down. S stands for soluble. SS stands for slightly soluble or sparingly soluble. It's kind of on the borderline. Insoluble is I, means it would form a solid for sure. And D means it would actually decompose. It would not form a solid, but it would not dissolve. It breaks down into some other compound. But so you could cross-reference charts like this to look for, oh, if I mixed iron with hydroxide, what do we get? Iron right here, scroll, 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 insoluble. Wham, bam, thank you, ma'am, you have a solid. But sodium chloride, soluble. Sodium hydroxide, soluble. Iron chloride, soluble. So we can use that table. Now, how are we going to do these reactions? We're going to need to represent these guys in a way that shows what is occurring. Remember, when compounds are dissolved in water, they can be classified as electrolytes or non-electrolytes, depending on whether they were ionic or molecular. Well, ionic compounds are capable of being separated into the cations or anions once dissolved. The key here is that once dissolved, we are going to separate aqueous ions into their cations and anion pair based on the fact that there are strong electrolytes. We will not be able to do this with solids, nor liquids, nor gases. They are going to stay together. But any aqueous solution can be split apart into their relative ions. Note this example. Note it very carefully. Lead nitrate breaks apart into lead 2 plus and 2 nitrate 1 minus. The subscript for the nitrate goes out front. There are 2 nitrates. The subscript goes out front to become the coefficient. We didn't call it NO32 or NO36 or N2O6. We called it 2 nitrates. Lead breaks apart and it's just lead 2 plus because it would normally be 2 plus charge to match the nitrate's 1 minus. I did not separate the nitrogen and oxygen. I left the nitrate together. That is for a good reason. The nitrate would not have lost all of its covalent bonds. It would have left them alone. We are only looking at the charges separating the ionic portions of these bonds. But with this idea of separating the ions, that leads us to a new way of writing the chemical equation called the ionic equation. An ionic equation or total ionic equation is one where all strong electrolytes, aqueous compounds, become split into their charged ions. Any solids, liquids, or gases are left normally, but any aqueous are now allowed to split apart. We'll treat them as thus. Now, why would we bother to split them apart? And that's because of what we see here. In this reaction here, we have lead nitrate aqueous and potassium chromate aqueous goes to lead chromate solid and 2 potassium nitrate aqueous. Now, splitting every aqueous part apart, lead nitrate goes to lead 2 plus and 2 nitrates. Potassium chromate goes to not K2 but 2K plus and chromate. Lead chromate, because it's a solid, stays lead chromate. And 2 potassium nitrates becomes 2 potassiums and 2 nitrates. Note the coefficient is applied to both potassium and nitrate. I say this from experience of people making stupid ass mistakes. With that in mind, note there is 2 nitrates on the left and 2 nitrates on the right. They are aqueous, they are -1. There's 2 potassiums on the left, 2 potassiums on the right. They are aqueous and +1. They do not change. They do not change charge. They do not change state. They are what we call spectator ions. They are ions that do not change. They are there to balance the charge, but they do not actively participate. They do as much for the chemical reaction as people watching a game from home. They do not affect it in any way that is meaningful. So they are not included. What we need to do is we need to take out all the spectator ions. Once we remove all the spectator ions, we get what's called the net-ionic equation. The net-ionic equation, remember, when we use net in math, it means the difference. What is changing? What is the net benefit? The net-ionic equation only shows the ions and compounds that directly participate in the chemical reaction. So, lead 2 plus and chromate 2 minus precipitate. They snap together like magnets, and they precipitate as lead chromate solid. That's the reaction we would observe when we mix those together. And thus, the net-ionic equation shows us what we should see. Now, some equations may not have a single spectator ion. Every ion may participate, and if that's the case, so be it. We leave it as is. But one of the key things is if a reaction is only made up of spectator ions, then no reaction occurs. What this means is if we can split all the atoms on both sides into aqueous and none of them change, not even a simple electron charge, there's no driving force. If there's no driving force, the reaction doesn't actually occur. We are showing something that happens, but it doesn't actually happen. Going back to the analogy I talked about in the last video of like a square dancing. You swing your partner and you swap partners. Well, dancing continues, you can swap back. That's the thing. If all partners are aqueous, they are capable of swapping as many times as they want. Once they form a solid, they now have a permanent partner. That partner, they're going to settle down. They're going to leave the dance. There's going to be no more dancing with other partners for them. They're going to just slow dancing off in the corner. They're not going to be swapping around left and right. So, but if they're allowed to swap back and forth, back and forth, back and forth, no reaction is actually taking place. So 2 examples I have here. Silver nitrate. Notice I already have the states of matter which make life a lot easier. Silver nitrate aqueous, sodium chloride aqueous goes to silver chloride solid and sodium nitrate aqueous. So sodium nitrate, silver nitrate, sodium chloride, silver chloride solid, sodium nitrate. You see one sodium, one nitrate, they cancel out. You're left with the reaction is actually silver and chloride ions form silver chloride solid. If I swap potassium nitrates with calcium chlorides to get potassium chloride and calcium nitrates, I break this apart and everything cancels out. Everything cancels out, even though I drew the chemical reaction. If there was no solid, it's not going anywhere. It's not going to roll down the hill. It's not going to magically make a reaction occur. So, with that in mind, let's look at this reaction. How do I do this? Barium chloride and sodium sulfate. I'm going to have to jump back and forth between this and my dock camera. Okay. So the first step is, I'm going to assume, which is pretty safe, that these are both aqueous. How do I write my chemical equation? I need to do a double displacement. So that means this is going to swap with here. Barium is group 2. So it's going to be 2+. Chlorine is group 7, so it's going to be 1 minus. Sodium is group 1, it's going to be 1 plus. Sulfate is 2 minus. Swap that. BaSO4, 2 plus, 2 minus. Bring them down. Simplify 1 to 1. Na plus, Cl minus. It's not Na2Cl2. It's NaCl. However, there's 2 and 2, so I have to put 2 there. Don't forget our rules of charges. Don't forget our rules of charges. So real quick, I'm going to jump back. Let's look at barium. Barium sulfate. Barium sulfate is insoluble. Sodium is soluble. Sodium chloride is soluble. So, what that mean? Solid. Aqueous. Said, I don't expect you to memorize those guys, but we go, next step. Ba, 2 plus, aqueous. This goes out front as the coefficient. 2 Cl, 1 minus, aqueous. Goes out front the coefficient. 2 sodium plus 1, aqueous. And sulfate, 2 minus, aqueous. I'm going to write the arrow and put the products below. Any solid stays solid. Do not break apart your solid. But any aqueous, so this 2 is applied here and here. 2 sodium plus aqueous. 2 chloride minus aqueous. And what do we got? Those cancel. And those cancel. So what we write for our chemical reaction is Ba2 plus aqueous and SO4 2 minus aqueous BaSO4 solid. Okay. And that's what we got. Let's see. That would be example. I'm going to go ahead and stop that here. In the last video, we're going to look at acids and bases and redox reactions. But we will be building on this concept. We'll be building on this concept. So let me do one more. I'll make one more from scratch that isn't on my slide. So let's look. Nickel chloride plus let's see. Let's see. I'll say potassium carbonate. Okay. All these should be aqueous. So let's go back to the chart real quick. Nickel is 2 plus, chloride is 1 minus, plus 1, 2 minus. We have nickel carbonate and potassium chloride. Potassium chloride is soluble. Nickel carbonate is insoluble. Potassium carbonate is. So, with that in mind, solid, aqueous. Breaking that down, nickel 2 plus, 2Cl minus, 2K plus, CO3 2 minus, aqueous, 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 aqueous. Nickel carbonate solid, 2 potassium pluses, 2 Cl minuses, aqueous, aqueous. Canceled, canceled. What we have is nickel 2 plus, carbonate 2 minus, goes to nickel carbonate solid. That is how we have to do that. Okay. That's where I'll leave you.